Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Surfaces.
So, thank you for the chance to speak here, and well, I really hope that I will impress you more with my work than with driving here. So, this talk is maybe too specific or too. It's a small. So local chromatic number is not studied very widely, but I hope that you will find it interesting. I think it's an interesting concept. And by the way, if you are intimidated by not knowing the meaning of any of those words on the title, then relax, I will explain every single one of them. And the talk contains part of my ongoing research collaboration with Gabor Simonyi, who is a colleague of mine at the Rényi Institute in Budapest. So, as I said, I will explain everything, even what a graph or a coloring is. So by graph, I mean simple undirected graphs throughout the talk. And proper coloring is I color the vertices in a proper way, so neighbors are not assigned the same color. And, well, you all know that the chromatic number is just the minimum size of set of colors that you can do this with. So here you want to properly color the vertices so that you don't use too many colors in total. In the local coloring number, you are allowed to use any number of colors, but you want to minimize how many colors appear in the neighborhood of a vertex. So this n of x means all the vertices connected to a vertex x, and you want to make sure that there aren't too many different colors appearing there. And you say it's a local k coloring if less than k different colors appears in the neighborhood of any single vertex. Less than or equal than k minus 1 because you somehow consider the color of that vertex. This is a proper coloring. So if you have k minus 1 colors in the neighborhood, then you have at least k colors total because that vertex has a different color. And so the concept is that you want to have locally as few colors as possible, but altogether in the graph you can use any number of colors. And so this was introduced by Erdos, Füredi, Hajnal, Komját, Rödl, and Seres exactly 20 years ago, but not much research has been done after that. So that's a very nice paper, and they prove some of the basic properties of this local chromatic number. They don't call it this way, but so again, local chromatic number is you want to minimize this parameter k. But later, not much research was done about local chromatic number up until in results in information theory. It turned out that this is in fact an important parameter of graphs. And by the way, I think that I mean it has some beauty, so properties of local chromatic number can be interesting. So some properties of, well, I call psi so chi is traditionally, this chi is traditionally the chromatic number of a graph G, and for this talk I use psi for the local chromatic number. So local chromatic number is at most as big as the chromatic number, because if you color the graph with like 100 colors, then in every neighborhood you can at most 99 of them, because the color of that vertex is not in the neighborhood. So that's the trivial part. Interesting part is that actually there are graphs for which this inequality is strict. We'll come back to that. From the other side, you have, this is the fractional chromatic number. This is a result of Klein and Seymour. That's a lower bound. So for many graphs where the chromatic number and the fractional chromatic number are close.
Are you going to tell us what the fractional chromatic?
No, I'm not. That's the one cheating. I will never use a fractional chromatic number in the rest of the talk. I mean, this is just to, I mean, some of you know what the fractional chromatic number is. That I mean, intuitively what this means is that for many graphs, this is a well-studied parameter, and for many graphs it happens to be close to the chromatic number, and therefore it gives you a good way to estimate the local chromatic number from below. But I will never use it. That's the last time this ever appears on the screen. So a trivial observation is that if the local chromatic number is 2, then the graph is bipartite. Well, that's not very surprising. If you just have a single color in the neighborhood of every vertex, then you basically, in any connected components, you can just have 2 colors in that coloring. So it's a bipartite graph. So nothing interesting is going on there. And this 20-year-old paper by Erdos and al., they proved that the local chromatic number can be 3, even though the chromatic number is arbitrarily large. So there is no strict connection. I mean, above the level of 2 where they are equal, above that there is no connection between the two other than the local chromatic number is less than or equal than the chromatic number.
So did they give a construction?
Yeah, they gave a construction. But there is a price to pay for this. If you really want to have a local 3 coloring of a graph that has a high chromatic number, and you need to use a lot of colors. I mean, a local 3 coloring uses at least this many colors. So the graph, I mean, in particular, has to be at least as big. I mean, this is doubly exponential in the chromatic number. So there are examples, but those examples are huge. I mean, if you want to make the chromatic number big, then you must start with a huge graph, and the local 3 coloring will also use a huge number of colors. And so this is an example for that. Actually, this is an interesting parameter. They have to, that the local chromatic number can actually be strictly less than the chromatic number. And sorry about this. Does not contain sign here. I mean, this is my first talk that I gave with that I'm giving with the computer, and took me a lot of time to prepare all the slides. I always push the wrong buttons. And I have no idea how to prevent this to showing up, but
That's not a problem.
maybe, yeah. So you will you will see that it will actually have a reason. I mean, there will be a line showing up where this actually means something in that line. Just don't know how to make it show up at the same time as the line does. So this is a graph that it's very easy to see that it's universal for coloring, local K coloring with M color. So what that means that this graph has a local K coloring with M colors. The M and K are the 2 parameters, and M is supposed to be much bigger, or at least somewhat bigger than K. And any graph with this property that it has a local K coloring with M colors actually it can be map to this graph in a straightforward way. So this is where the not in sign is used. So you take the set of colors, that's a set of size m, and for any vertex, you actually want to tell what its color in the local K coloring is. That's just A, which is an element of the set of colors. And then you want to say what are the neighbors, what colors do the neighbors have. And that's a set of K minus 1, size K minus 1. And of course, it must be a proper coloring, so the set of colors of the neighbors should not contain your color. And then basically these are the types of the vertices you can have in any local K coloring with M colors of any graph. But you can make this into a graph by just connecting two. If they can be connected, that really means that the color A there is allowed as a neighbor of this vertex. So A is in the set of allowed neighbors, and vice versa. B must be an allowed color for the first vertex, and then you connect them. This is an example of a graph that distinguishes local chromatic number and chromatic number. It's easy to see that the local chromatic number is K by design, basically. You can color everything. You can color the pair AP by A, and then that's a local K coloring. And you can work out that if you put in the parameters 5, 3, this is basically the smallest parameters you can put in. As I mentioned, if the local chromatic number is 2, then it's a bipartite graph, so nothing interesting happens. And for 3, 4 is also not interesting. It's a 3 chromatic graph. But if you put 5 and 3, then you get a 4 chromatic graph. So that's probably the smallest example of a graph where psi is less than the chromatic number. It's certainly the smallest of this universal family because these are the smallest set of parameters for which this works. But this has 30 vertices. I didn't prove that this is actually the smallest example. Actually, we have another example, a non-isomorphic graph with also 30 vertices where the chromatic number is bigger than the local chromatic number. It's not 3 and 4, but 4 and 5 there. But I don't think there exists something with a smaller number.
How does this graph look?
Yeah, that's my very last slides. I will give you a very nice look. But it's kind of if
No. It needs measuring. But I'm just wondering.
so. I mean, in general, for U53, now we have a very good understanding how it looks, and I will come back to that. In general, for UMK, I don't know anything that better describes it than this definition. I mean, each has. So UMK is defined by the vertices are pairs. Vertices is given by a color and then a set of colors. Set of colors of size K minus 1. And then two of these are connected if this two property holds. But the way you think about it is that you want to think of the first color as the color of that vertex at the local K coloring, and the set of colors is the color of its neighbors. And if you think of it, it's clear that these are the vertices that you can connect, because you don't want to connect this vertex with this vertex if A is not in Q, because then you would have something in the neighborhood of this vertex that does not belong there because its color is not in Q. So this is about local chromatic number, and
This is stupid, but so I see that I'm allowed to connect them if A is in Q and B is in P, but do I have to connect them?
no, certainly not. Actually, if you just take any graph that has a local k coloring with m colors, you can have more than one vertex with this type. I mean, you can say that this is the type. Also, you can have a type where the color is A, but the neighbors have colors with cardinality maybe less than k minus 1. So you can have more vertices, even for the same vertex type, you can have many. And no, you don't have to connect these if you can. I mean, but this is universal in the sense that any graph that has a local k coloring with m colors, you can just have a homomorphism to this graph. Meaning you can take any vertex, you take its color, the neighbor's color. If it happens to be a set smaller than k minus 1, then you extend it any way you want, and then you map it to this vertex. And in particular, if you take a subgraph of it, I mean, you delete edges, then also that's a homomorph. The identity gives you a homomorphism to this graph. So this is universal. This is the
I'll find all the graphs I'm looking for as subgraphs of this graph.
as homomorphic images of. You can actually collapse vertices. I mean, if you have, it's the same thing as you saying that a graph is 5 colorable if the K5 is if there is a homomorphism from that graph to K5, and the same way local chromatic number can be explained as something has a local chromatic number K if there is a homomorphism from that graph to this, except that in that case you have to make M infinity in order to avoid. I mean, if you really want to make it describe all graphs with local chromatic number K, but if you want to describe only graphs with local chromatic number K that has this local chromatic coloring with M colors, then this finite graph will do.
M equals K to the N.
Fun?
And you choose K equals M to the N, where N is the number of vertices here.
Oh, you can choose.
I mean, M equals K.
M equals
I mean, given K, there is no way to bound them. I mean,
With N, if you say if
you can choose, if you know N, then you can choose Mn. I mean, there is no more, I mean, certainly you won't use more colors than the number of vertices. So if you just want to have one graph G with N vertices, then you can choose M to be N.
particular, yeah.
But even if you fix K to be 3, these graphs tend to be more complicated as you increase them. In particular, their chromatic number grows as very close to log of this M. So you increase M, it just grows. Okay, so for now, we leave local chromatic number and go to surfaces.
One more question.
Yeah?
Local chromatic number is just for every vertex, you look at the chromatic number of neighborhoods. So how would that relate to the parameter size?
Oh, you mean the chromatic number of the neighborhood. So if it's a triangle-free graph, then you would get,
That would be
it would be very small. So certainly this, I mean, there is a one-way correspondence. If the neighborhood has a high chromatic number, like 10, then the local chromatic number of the entire graph is at least 11, because you have this vertex, plus in the neighborhood you have at least 10. So there is this correspondence. But the other direction, there is no correspondence. You can have all the neighborhoods being just isolated vertices if you don't have a triangle. But still, the local chromatic number can be high.
Psi can be allowed.
Yeah.
How high?
How high can be a local chromatic number of a triangle-free graph? That's a good research question. I mean, it was certainly studied with respect to chromatic number, and my guess is that you just work and prove the same bounds for local chromatic number, but I might be wrong. I never studied that. But actually, when you look at the coloring, so sometimes, as I explained, there is a difference between the local chromatic number and the chromatic number, but I mean, it's not a question of random graphs, but like just typically there is no difference. Typically the best local coloring is just the best coloring. I'm not sure what I mean by typical, but
The
Fractional chromatic number is unbounded for triangle tree. That's a lower bound. Because the
I didn't break my
largest
promise. I never
number
mentioned
is
fractional chromatic number. It's lotsy.
can be root 10 at least.
He never follows rules.
Fun? No. So if you have any more questions about local chromatic number, then ask now, because for the next few slides, I will do surfaces and quadrangulations. Okay, so this also shows how primitive my ways are with computer drawing, but this is my hand drawing of a Klein bottle here. So surfaces, by surfaces I mean compact, no boundary, two manifold. So like the sphere or the torus or things like that. And as we all know, these are characterized, there are two infinite sequence of them. Like orientable, starting with the sphere, and then you add handles to the sphere, you get torus, double torus, torus with 3 holes, 4 holes, and so forth. And the other sequence is that you also start with the sphere, but now you insert maybe Möbius strips. And then if you insert one of them, then you get the projective plane. 2 of them, you get the Klein bottle, and lower they don't really have names, but you can insert any number of Möbius strips into a sphere, and then you get the non-orientable surfaces. So these will be, when I mean surface, I mean one of these, and mostly one of the non-orientable ones, because those are more interesting from our point of view. And now comes quadrangulation. So quadrangulation is just the graph embedded in the surface. So it's really a planar graph in the sense. I mean, if it's embedded in the plane, it's a planar graph. So no crossing is allowed. This happens to be a quadrangulation of the plane, or in other words, a quadrangulation of the sphere. That's the same thing. And this lower one, as a square grid, I mean, you can imagine this is joined up, and then it's a quadrangulation of the torus. So it's locally bipartite, meaning that every face has an even number of edges, namely 4. And therefore, it's very easy to show that every circle that cuts the surface into 2 parts actually is even. So that's what locally bipartite means. And so every circle in the sphere cuts the sphere into 2 parts. So therefore, every circle is even. So any quadrangulation of the plane is bipartite. But it's not necessarily true for other surfaces. Like for the torus, you have this grid, and it's not necessarily bipartite. It's basically the product of 2 cycles. If one of the cycles happens to be odd, then it's not a bipartite graph. What you have is that in the torus, you have those circles that do not cut the torus into 2. I mean, even if you cut along the circle, still it's a tube, and it's connected. So therefore, it doesn't have to be even, and sometimes it's not even. And the surprising theorem of Young's is that take any quadrangulation of the projective plane. So this is why we stick to non-orientable surfaces, in this case the projective plane. This is its chromatic number, 2 or 4. 2 is not very surprising. I mean, you can do it in a bipartite way, and you get the bipartite graph. And all the other ways are 4 chromatic, which is an upper bound and a lower bound. I'm not so interested in the upper bound, but the lower bound part says that it's not 3 chromatic. As soon as you have an odd cycle, the thing is at least 4 chromatic. There is no way to 3 color quadrangulation of the projective plane unless it's bipartite. And you will soon see a very nice and elegant proof of this, which is not mine, but it's a generalization.
The upper bound has nothing to do with four colors.
The upper bound has nothing to do with the four-color theorem. It is true, and I'm not sure how they prove it, but I'm more interested now in the lower bound. It's
Doesn't it have a, doesn't the, must have a point of degree of 3?
fun.
You get all faces 4 and all degrees 4, you need a torus.
Yeah, I mean, yeah. You can have all faces 4 and all degrees 4 in the Klein model, which is also Euler characteristic 0. Beyond that, I mean, as the genus increases, the average degree can go up. Yeah, but for the projective plane, you're right. I mean, you cannot. Yeah, so that's an easy proof for the upper bound right there.
Not necessarily. You remove this point and it's not a quadrangulation anymore. But I think the rest also has a point of degree.
Yeah, I don't think that there can be a subgraph with all degree, at least degree 4. It's just okay. So there is at least a sketch of the proof right there. Yeah, I didn't check that part, but I'm more interested in the lower bound because somehow these small examples are like, what's the chromatic number of the torus? I mean, that's the chromatic number of the highest chromatic number on any graph embedded in a torus. And that happens to be 7 because K7 can be embedded in it. But that's somehow cheating. It's just this too small graph. And as long as you really consider graphs that are kind of pair representing the surface, I mean, it's not just this small complete graph that happens to be there, then the chromatic number of the torus drops, and the chromatic number of all these surfaces will be 4 or 3, depending whether we'll see it in a moment. So, but I mean, this 4 or 3 dichotomy is what really matters if you disregard small graphs.
How about if I cut my surface and therefore gave it some boundary?
Yeah.
Okay. Then could you get this by cutting it and getting the Mobius strip? Could you get a lower bound that way? Because if you cut it, you would get a lower bound because it might not match up, so you might need more.
If you cut it, you get.
Right, wouldn't you get a lower bound if you cut it because then you might?
I don't.
Because
No, it's if you even remove a. I mean, if it's a high, if you just remove a single. I mean, all these graphs are minimal. I mean, color critical. I mean, if you remove a single edge, the chromatic number will drop. It's really about quadrangulation of a projective plane that makes it for chromatic. You really kind of need every square there. So the generalization by two set of people, Archdeacon, Hutchinson, Nakamo, Negami, Ota, this is one paper, and Mohar and Seymour is another paper, independently, same time. And the generalization they proved is basically the same thing, but instead of the projective plane, the same thing happens for all non-orientable surfaces, except that there is some parity constraint here. The parity constraint is not as simple as that. I mean, there I can say that theorem is that if the quadrangulation is not bipartite, then the chromatic number is at least 4, or exactly 4. And here it says something like that. If a parity constraint is satisfied, then the chromatic number is at least 4. And the parity constraint is a bit more complicated. You take you can have, so yes, oops, it's not a good idea. Here's the Klein bundle. If you cut it along a circle like here, then suddenly the entire surface is orientable. So that's what I call an orienting cycle. You cut it along a cycle and hope that the remaining thing is orientable. If you find that cycle actually you find such a cycle for every surface. It's not unique, not even homotopically, but you will find such cycles. And if one of these cycles happens to be a graph cycle, and you can just check the parity of that cycle, and that gives you a parity. And if the parity is odd, so there is this odd cycle that cuts the surface into an orientable thing. Then I call that an orienting cycle, and then the theorem applies. And clearly that generalizes the Bob's theorem, except for the upper bound, because
And then you do get a surface with boundary when you do that.
you get a surface with boundary, but actually you want to color the original graph. So you don't allow just coloring the Möbius strip. You want those colors to match up.
You want the things that
Yep.
are on either side of that to match up properly.
Yeah. So clearly, if you what is the thing with the projective plane is that its fundamental group just has one non-trivial element. It's one non-trivial cycle in the graph. If that non-trivial cycle happens to be odd, then that's an orienting cycle, and you can apply this theorem. If that cycle happens to be even, then there is just no odd cycle. I mean, that was the only non-trivial cycle, and all the trivial cycles are even because this is a so I don't want to use locally bipartite because that somehow refers to local coloring, and I use local coloring for something else. But it's on the surface, it's locally bipartite. So everything that is a trivial cycle, you don't care about. But what's the essence of this is that this theorem doesn't look that nice as the previous one, but it finds the good parity constraint. This is the parity constraint for all and that's the most that you can say if you have an orientable surface or maybe a non-orientable surface where this orienting cycle is even. In all those cases, there are 3 chromatic graphs there, so that you cannot say anything about anything as nice as here. And so I want to show this is a very, certainly not mine, but it's a very nice proof. The first set of people's proof will be reproduced here. And I try to do it really fast. So what I really want to say that it's more general. It finds a multicolored face in any proper coloring. So it's very similar to local chromatic number in the sense that you don't care about how many colors is used. You just want to show that if it's a proper coloring, then you locally find 4 colors. But locally here means that on a face. And there will be a multicolored face. It's not exactly the same as locally in the local chromatic sense. But this is what the proof does. So assume that the colors are numbers, and now there is a smaller and a larger number, so you can orient every edge towards the larger number. So that gives you an orientation on the edges, and then you can orient the faces. And you do it by orienting the surface. You cut first along the orienting cycle, and there things will not match up. But for the rest, it will be consistently oriented. So if this is oriented this way, then this will still be oriented.
So far, that just has to do with the cycle that you cut it with, not
Yeah.
with not with the directed graph.
No. So these are two directions, and then they will interact with each other in a second. But one depends on just the coloring, and the other depends on just the circle that you cut the surface with. And so you see that at the circle, you will actually misalign this. It has to be that at the circle they don't match. If they match at the circle, if they match at one edge of the circle, they have to match at every edge of the circle, and then it's an oriented surface. I just assume that the surface is not orientable. So these things do not match at the circle, but match everywhere else. And so now I just want to say that this edge of this square here is a good edge because the orientation of the edge and the orientation of the face matches. It's consistent. Both are oriented this way. And the same with the same edge and the other side. But for example, this edge of this circle, if this face is an inconsistent edge because the edge is oriented this way, the face is oriented oppositely. So you just want to consider the number of consistent edge face pairs minus the number of inconsistent edge face pairs. And that's double counting. You can count by faces or you can count by edges. If you count by edges, then these red edges contribute plus or minus 2. This guy contributes plus 2 because it's consistent with both orientation on the two sides. This also plus 2. But you can have minus 2 too. But that's the only thing that can happen. And for every other edge, it's 0. I mean, this edge will be consistent with this face and will be inconsistent with this face. So what you have is plus minus 2 an odd number of times. And that's a non-zero value. And if you look at faces, it's a very simple case analysis that only these faces can contribute non-zero. If you have these kind of faces contribute 2 or minus 2 depending on how they are oriented, and that's the only case. In this case, you have a smaller color, a bigger color, an even bigger color, and the biggest color here. So all the colors are different, and these are the only type of face that actually contributes non-zero. So that's the end of the proof. There is a multicolored face. Okay, so what we want to do is to generalize this result to local chromatic number. I want to say that the same holds with respect to local chromatic number. If this parity constraint is satisfied and there's a quadrangulation of a non-orientable surface, then not only is the chromatic number at least 4, but the local chromatic number is also at least 4. What you really want to do is these proofs give you a multicolored face, multicolored circle of size 4. And instead you want to find a multicolor star of size 4. Neither is stronger than the other. These are different things, but somehow this has a simple proof that I just showed you. This seems to be more involved. Forget about that remark. So I guess I have to give you the results that we have. So first, positive results. The Young's and its generalization result generalizes for the projective plane and the Klein bottle. You don't have locally 3 chromatic triangle or quadrangulation of the projective plane or the Klein bottle that has this odd orienting circle. And so if the orienting circle is even, then both of these values are 3. If the orienting circle is odd, then both of these values are 4. So they are equal. And so you see that this proof that I just presented, it didn't depend on the genus. It didn't depend on what kind of non-orientable surface you started with. This proof obviously does depend on it because it does not apply for any non-orientable surface. We have a counterexample. We have 3 chromatic quadrangulations of a non-orientable surface of any genus, at least 7. Genus is just how many Möbius strips you put in. So genus 1 was the projective plane, genus 2 was the Klein bottle. And if you put enough, at least 7, then we have counterexamples. We have examples where the local chromatic number is 3, but the chromatic number itself is definitely 4 because it has an odd orienting cycle. And it's open. Yeah, it's not clear, but it's true. Well, it's not that hard to prove. Orienting cycles are many. I mean, there are many orienting cycles, and their parity will all be the same. Actually, what you can do, that's also a proof of this statement, is that you can just take, instead of orienting the surface so that it's only inconsistent along a circle, you can just orient the faces as you want. just any way. I mean, for every single quadrangular face, you orient it this way. Maybe for the next, you orient it the opposite way. And then you just count how many edges there are where this orientation is inconsistent. And the parity of this thing is an invariant. Because if you reverse the orientation of a face, then you reverse 4 edges, so the parity doesn't change. So this parity is actually an invariant of the graph. And one way to visualize this parity is by an orienting cycle where you make every face orientation consistent except for a smallest number of edges that's possible, which is usually a circle. But you can define it this way, and then it's clear that it doesn't depend on the orienting cycle. It's just an invariant of the graph.
How about genus 3?
So, I didn't say that? Yeah, good point. So it's open for genus 3, 4, 5, and 6. So this is all we have. So this is a negative result for big genus. This is the only positive result we have. Everything in between is open, even if I didn't put 3 on
Do
the...
you have a conjecture about any of them or no?
I'm not sure. I have one more result that I can show, is that these examples for genus 7 uses the fewest possible colors. If you just have 4 colors, and it's not possible to have a locus 3, anything that is 4 chromatic, if you, more general, if you have a graph and you use the optimal number of colors to color it, then it's not a good local coloring. It doesn't do better than the chromatic number, because in an optimal coloring, every color class has a vertex that sees in its neighborhood all the other color classes. So you cannot use 4 colors to get the local 3 coloring of a graph that is not 3 colorable. But this is as good as you can get it. Our example uses 5 colors. And I can show that all in this undecided cases, if there exists a counterexample, it must be more complicated. It must use more than 5 colors that I can show. So that's an indication that maybe 7 is really the threshold. But actually, I don't think so. I think that maybe it's around 2 or 3. Maybe it's also true for 3, but not for 4. But this suggests that maybe 7 is the right threshold. So I'm not sure. Okay. So how much more time I have?
We started late, I don't know, 20 minutes?
Oh, that's a lot.
Okay.
Okay,
Well,
so
that's also fine.
no, I was worried about like maybe you say that 0 or something. So actually, I mean, local chromatic number is not a well-studied thing, and I think these results will be interesting, but a big part because the techniques involved. I mean, say there are nice things that are involved in the proof from group theory, and so I want to show some bits of the proof. I will not give a proof like I did with the Archdeacon et al. Paper, but I will give a sketch of the proof. So, sketch of the proof of the positive results. I mean, the negative result is just a counterexample. I mean, you draw a big enough graph at 7 genus, whatever, and then it turns out that that's a counterexample. And what about the positive result? So the positive result uses this. You have a quadrangulation like this one. I mean, this is obviously just a part of a quadrangulation of some surface. And then you want to put labels on the edges that somehow cancel out. I mean, this is what happened. Like there was this direction which somehow positive, negative labels. But it turns out that it's nicer to use...
That 3 has, wait, no understanding. You know, lots of things the same color in their neighborhood.
Colors that are neighbors? I hope not. I mean, the numbers represent colors. This is a proper coloring because 3 is not equal to 5.
Yes, good, okay.
If there are 2 vertices that have
No,
the
there
same
aren't,
color,
there aren't.
it was my mistake. There shouldn't be.
No, it's fine.
But these can have the same color because these are just opposite vertices of a face. Okay, so now what we... And by the way, it's a local 3 coloring so far. So like this 5, only 3 is ones and threes. And so it's better not to use the graph itself, but the medial graph. We put a vertex in the middle of every edge, and there you get another embedded graph in the same surface, this one. So there is this red graph where so every middle point of an original vertex will be a new vertex of this red graph, the new graph, which I call the medial graph. And I put labels on the edges of this new graph, and they come from the labels of the edges of the vertices of the old graph. So there is this 5 and 2 here in opposite vertices of a face. So look at every face. Every face you have, inside every original face, you have this quadrangle of the new graph. And you take two opposite vertices of the original face. These two colors will be put into the label of this edge. So this edge somehow is a transition from color 5 to color 2. And well, the other edge here is also color 5 to color 2. And you think of it as a transition, it's 5 to 2. And this is why I oriented the red edges, but these are really for reference purposes only. So if you go on this edge, it's 5 to 2. If you go on the other direction of this edge, that's 2 to 5. So in my notation, this 25 is the inverse of this 52. So this is a labeling. And now what we can do with this labeling is, well, first of all, there are the 1-1s. I mean, transition from 1 to 1. I didn't even put that label up there because that's the identity. I mean, there was no transition there, basically. And as I said, 13 is the inverse of 31. So it really means a transition from 1 to 3, and this is the reverse transition from 3 to 1. And the main thing is that the same number of, say, 1 to 3s and 3 to 5s on every face. Why? Because there are basically two types of faces. One is the quadrangle inside the face, and then it's very simple that the same transition 5 to 2 goes to 2 to 5 on the other side. If there is the 1 to 3, then it's 3 to 1 here. So it just cancels out. And there is other type of face where it should not be the case in general, but now we have a local 3 coloring. Therefore, everything that appears in these edges are colors of the neighbors of this vertex. And there are only two of them. So in this case, it's just 1 to 1, 1 to 3, 3 to 1, 1 to 3, 3 to, what is it, 3 to 1, 1 to 3, 3 to 1. So there is not much variety going on there. In general, there could be 1 to 2, 2 to 3, 3 to 1. But nothing like that happens because it's a local 3 coloring, so there are only two types. So clearly, if you have a cycle with just two labels, that exactly as many transitions from 1 to 2 as 2 to 1. I mean, it just cancels out. So that's something that can be used to show that basically it's locally nice. Everything cancels out locally. And if you have a cycle, then maybe this cycle labeled 1, 2, 3, 2, 4. You want to associate with this another cycle of the red graph and then show that the labels there somehow correspond to these labels. So this is just a small part of the graph. And basically what you do is go from the middle point of the circle to the next, to the one edge of the circle, to the middle point of the next edge of the circle. And in that you go around that vertex. And it's basically, in this case, it's a transition from 1 to 3. It goes to 1 to 3 and then 3 to 3. So, and also in this more complicated case, it goes from 3 to 4, then 4 to 3, then 3 to 4. But the net effect of this thing is you can just read it from the cycle. So from the cycle, colors on the cycle, you can find the colors of the corresponding cycle on the medial graph. So you see 1, 2, 3, 2, 4, and then you have the second neighbors. 1 to 3, 2 to 2, 3 to 4, 2 to 1, and 4 to 2. And so the hope was that we can use the same kind of proof technique to show that in this every cycle, this ij labels and the ji labels will be the same, and this is easy to prove actually. And then we show by this that the orienting cycle, I mean, this is easy to show for an orienting cycle, and then you show that, okay, then the orienting cycle actually has to be even. But that's the bad news is that this doesn't imply that the orienting cycle has to be even. This is the shortest counterexample. It's a cycle of length 9. The corresponding second pairs, you just count the number of 1 3s, which is 1, and it exactly agrees with the number of 3 to 1. So it's a bad start. I mean, it's a proof idea that didn't work. So what could we do? We decided to use a non-commutative edge labels then. And instead of just counting the labels, you actually consider them as group elements, and then you multiply them together in some group. Now, what that group should be, I mean, it should be as free as possible. Of course, the generators are the pairs, again with the agreement that 1 to 3 inverse is 3 to 1. And we want that this phase would cancel out. And it's a 1 to 2, 3, 1 to 4, 3 to 2, 4 to 1, 2 to 3. So we actually want these pairs to commute. And in general, we want pairs to commute if they are disjoint. They are not disjoint, then they never come up in such a phase. And in the phases around vertices, there is just no problem. Nothing have to commute. So this is the graph. This is the group that we considered. These are the generators, and these are the defining relations. So the defining relations are just that some pairs of generators commute. Any group that is given by generators and defining relations, where the defining relations are this simple, it's just a pair of generators that actually commute, is called a semi-free group.
But you have pairs that don't.
So non-disjoint pairs do not commute. So 1, 3, if every pair commutes, then it would be a free abelian group. But these pairs do not commute. It has a pretty simple combinatorial structure, these semi-free groups. So it's easy to work with them. And the thing is that we don't have this problem anymore. If you start with a knot cycle, then you have something and that never cancels. In this case, it doesn't cancel because, say, 1, 2, and 2, 1 are inverses of each other, but they don't cancel because they don't commute with these things in the middle, because they are not disjoint. If this was 5, 4, and 3, 5, we would be in bad shape. But they don't. But in this case, they don't cancel. And it's easy to show. Well, it's a combinatorial argument, really not very hard to show that if you start with an odd cycle, meaning an odd cycle, obviously no consecutive elements have the same label, and then you produce these pairs, second neighbor pairs from it, then in this semi-free group, it will not cancel. And so what we have the fundamental group of non-orientable surfaces of genus G. It has been studied. And these are just the group of
It's easy to show that this odd cycle doesn't cancel. I mean, it's,
I gave it to a graduate student to work out for himself, and he did. So I don't think it's really hard. It takes something. But I mean, it's more. I mean, yeah, that doesn't say anything, because I just think that I mean, even before that, I thought that he would. I mean, it's not that hard. I mean, there are congenial graduate students, but it's not that because, I mean, just think that it's an exercise. You can, I mean, anybody can do it. So, what is the fundamental group? Is just the group of cycles. To be precise, it's a cycle from a given starting vertex, and then you can multiply 2 cycles by going one after the other, and you say that the cycle is the same as the other cycle if they are homotopic. So that's the fundamental group, and the fundamental group of surfaces have been studied extensively, and this is what describes them. They are, if the genus is G, then there are G generators, and this is the only defining relation in the group. The square product of the squares is 1. Nobody really considered orienting cycles that much, but if you want to consider orienting cycles, then this is how to get one. There are many orienting cycles, but this will give you one. So if you just take this product without the square, that gives you an orienting cycle. So what do we have now? We have that the labels on facial cycles in the faces of the red graph cancel. So as a consequence of that, a product of the cycle is really determined by the homotopy class. If you just move, so it's very simple to see that if you just have a cycle on the surface, and then you move the cycle a little bit, meaning that there is this quadrangle face, instead of going on this side, you will go on the other 3 sides. And what you change the product of the labels is just basically the product here. And if that cancels out, then the new product will be the same as the old product. So really, the product of the labels is independent of which specific graph representation you take of that element of the fundamental group. And what this means is that it's a fundamental group maps to the group of labels, in this case, this semi-free group. So there are generators that map to some values, AI maps to BI. And what we have is that the square product of AIs were 1. So the square product of BIs is again 1. And what we have is that if you have an odd orienting cycle, then B1 through Bj is just the image of the orienting cycle. And if it was an odd orienting cycle, then the labels do not cancel out. That was this combinatorial argument. So we have that the product of these guys is 1, but the product of these guys is not 1. So can this happen? In the projective plane, it would mean that something is not 1, but the square of that is 1. Well, that happens a lot of time in groups, but it doesn't happen in semi-free groups. So a result of Bodish in 1977 is that there are no torsion elements, no elements that are not 1, but some power of it would be 1. It just doesn't exist. Actually, this is very easy to prove. So I can quote him, but it's anybody can prove it. So as a result, quadrangulations of the projective plane satisfy that the psi is also at least 4. So it equals to the chromatic number. Klein battle. Genus is 2. You have 2 elements. Square product of squares is 1, but the product is not 1. Another paper of the same author, and this one is a bit more involved to prove. He actually proved that if you take a semi-free group and any 2 elements, they either commute, or if they don't commute, then they are as free as you can get. There is just no relation between them. Well, if they do not commute, then in particular, this is not a relation that they would satisfy. If they do commute, however, then this guy is the square of that, and we were there already in the previous slide. That never happens in semi-free groups, that the square of something is 1, where that guy is not 1. So again, we have that the quadrangulations of the Klein bottle satisfy, again, if the orienting cycle is odd, then the local chromatic number is 4, and also the chromatic number is 4, otherwise both of them are 3. Genus 3, well, I didn't find the correct paper of Bodish for this one yet, but that's an interesting research problem on its own. So does the square of product is 1 implies that the product is 1 for 3 elements? So this is open. If the answer to this is no, that solves the question for genus 3. If the answer of this is yes, then you still have to work on it to actually implement it with a graph. Maybe you can, maybe you cannot. My guess for this is, if the answer for this is that that this does not imply, then the answer for the quadrangulation question is also negative. I mean, that's my guess. And this is really the essence of the problem. And for genus 7, here is this very nice example of 7 elements of which the square product is 1 and the product is not 1. So you might wonder how we got this 7 elements. So it took a very big piece of paper, and then we reverse engineered the graph. There was this example on the genus 7 non-orientable surface. We really had to find the basic generating elements of the fundamental group, and it took a lot of time to reverse engineer these elements.
So then the question is, so if you reverse engineered this from the graph, how did you get the graph?
Okay, very good question. So this is my last slide here. This is how we got the graph, and this also comes back to what U53 looks like. It turns out that U53 actually looks very nice. But this is not true for the general universal graph UMK. But for this one, it looks very nice. Around the vertex, it looks like there are 2 quadrangles around it. So 1, 2, 3 is just a generic element. Color is 1. The neighbors have color 2 and 3. And these are the 2 quadrangles it is in. Quadrangle, I mean quadrangle with 4 different colors. So 1, 2, 3, 4. And this is 1, 2, 3, 5. And then there are 2 hexagons in which it is also involved in. And that's basically it, except that the hexagons have all the main diagonals also part of the graph. So these, if you draw this, then this is not actually nicely embedded in any surface. If you remove these main diagonals, this is easy to check, but these edges are set apart by being part of a triangle. Actually, these 3 vertices form a triangle. It's the same 3 colors, but different one is decided to be the main color, and the other 2 is the neighbor. So if you remove these edges, then you have this very nice thing that is locally, not quadrangulation, but it locally embeds into some surface. And then you just have to figure out what surface it is, and it turns out that the Euler characteristic is easy to figure out, and it's -5, and the only surface with Euler characteristic -1 is the genus 7 non-orientable surface, so this is it. But in order to make
I'm confused about why you were able to look at something without a quadrangle, not to do the quadrangle.
Yeah, so that's not fair. You're absolutely right. This is not a quadrangulation of any surface. This is quadrangles and hexagons, right?
Right.
So you want to actually add back one of the 3. I mean,
Right.
if you just add back 1, then this hexagon will turn into 2. But it's not as nice a picture because I can't tell you consistently which one to add. So just any one of them you add back, you get a quadrangulation of the, and that's the quadrangulation. That is a quadrangulation of the genus 7 non-orientable surface. And it clearly is, there is a
So it's not
local
unique.
3 coloring.
So the
No.
generators is not unique because
No.
I have 3 ways of doing it there and 3 ways of doing it.
Oh, well, lots of ways where it's not unique, because then you can decide where to put the, I mean, the way to choose the generator set for the fundamental
And then
group is
there I
also
can
not
take my
unique.
cycle and
Yeah, there are lots of ways. And then this thing here actually was kind of optimized for shortness. I mean, I guess you didn't notice, but these are very short expressions. The original one that we got were much longer. So, and these graphs are nice. I mean, these are, as I said, as all quadrangulations of non-orientable surfaces. These are, that's not true for big quadrangulations, so I didn't say that this was big enough. But in this case, it's true. All of them, no matter how you put back one of the 3 edges here, are color critical. If you remove one edge, then the chromatic number drops to 3. And these are all the color critical subgraphs of U53. So this is basically pure luck. I mean, we know very little. Maybe this was the smallest example where we know that psi was less than the chromatic number. And then we noticed that this actually is a quadrangulation, or almost. You just have to drop 20 edges, and then it will be a quadrangulation of a surface. So it's pure luck, and I'm not sure how to. If there are examples for smaller genus, I mean, you might want to do something smarter. I mean, luck doesn't always work. So this is it. Any questions? Thank you again.